Taking a look at resistors, and we're going to specifically look at resistors in a circuit, and that circuit can be arranged in two fashions. We're going to look at what's called a series circuit and a parallel circuit. And there are a lot of laws that are going to apply depending upon whether the circuit is in series or in parallel. So we're going to first start by looking at the two types, or an image of these two. So first, series. If elements are connected in series, it means that a portion of the circuit is a single path. A single path. What does that mean, a single path? Look at the diagram on the right of series and try and describe what I'm getting at with a single path.
Like one thing connects to the other?
Yeah, one thing connects to the next, which connects to the next. Now, if you look at the parallel path, though, what do you notice in the parallel path? What do you notice when you look at the parallel path? Cooper.
Well, the energy is going in one direction.
Okay, it's going in one direction. What else? What else? What's the difference? Look at the two circuit setups. What do you see as a difference, honestly? There's not much difference. There's one thing that's pretty stand out. Kim? No? No? I mean, focus on this, Kim, right?
No, I have on this one.
I don't know. I thought you saw a hand as well.
They're
Joey?
connected in different ways, so like it's going on top of each other.
Okay, they're definitely connected in different ways. Good. That's the first thing we'll notice. How are they connected differently?
One is one, one is horizontal.
Let's just add to the diagram.
But are those light bulbs?
Those are all light bulbs, yeah.
So when you said that one thing connects to the other, what is the thing?
They're light bulbs.
Okay.
Right? What's the difference though in the way they're connected?
One's horizontal.
They have been just that is divided.
Like if I were to follow the flow of electricity in the series circuit, I would outline it as follows. Ready?
Now.
Energy goes this way, into the bulb, into the bulb, into the bulb, into the bulb, back out. Agreed? Yeah. It looks like one path. Think about fluid flowing in pipes. Now, what about the parallel setup? Would it go that way?
No.
What would happen? It splits. Yeah. What are those called? Where two pipes come together. Or two roads coming together. There's several words you could use, so give me some samples of things where they come together. A merge, that's one way. A crossroad. A junction, another word, like a junction. Have you ever a junction of two roads is where they really intersect? So here what happens is this. The electricity flows out of the source. It hits the first junction and it splits. Part of the electricity goes into the first bulb. The other part, though, goes into the next, and then that part that remains splits into the second bulb, and then the other piece goes into the next. Then that splits into the third bulb, and that last part goes into the fourth bulb. In this case, there are 4 bulbs. However many resistors there are, it splits that many times.
Then equal distribution in the electricity.
That's what we're going to discuss and derive, so I'm going to hold off on that. Because we're going to show where that comes from, actually. That's the interesting part of the section. So we're going to figure out, how does the voltage split up? How does the current split up? What physically happens to the electrical signal that's going through the circuit if it's in series versus parallel? That's really the question of the day. Okay, what Johnny just asked there. So let's go into a little bit of the math that is involved here. So we understand the idea, though. Series is one continuous path. Parallel, there are junctions where that current splits itself off. Now, statement being true, let's take a look at series. So let's read this for us. Dirk, nice and loud. Read what we got for current in series, just the current piece.
Current across each resistor is the same length of flow rate of water through a pipe.
So if water is going through a pipe, and at several locations along the pipe length, you have these little gates, they're called valves, that allow you to turn the water on or off. If you've ever looked at the piping system, or the plumbing system, in any sort of system, you'll see their little bends. And you'll see a pipe like this, and on the side of the pipe, what you're going to see is a little lever. If the lever is this way, it turns the flow off. If the lever gets rotated like this, so that it's drawn, I'll draw it in red or blue, so that the lever is this way, it turns it on. It's a fun fact you should know about like your house. If there's ever like a leak and a pipe bursts, you want to find a little valve that is probably parallel to the pipe and make it perpendicular. It would turn the flow off. So even if you have these little valves along the pipe, what you'll notice is that if all the valves are turned open, right? So if this next valve is also open, and the next valve is also turned open, assume they're all parallel, they're all open, what will happen is the flow of the water will flow through the circuit, and there'll be the same amount of flow at each location, assuming they're all open, okay? Water flows out of the pump, it goes through the pipe, it has the same flow rate until it returns, or until it exits the house, or whatever it was that you're drinking. Now, it's the same thing for current. If current is in series, like a pipe, with several different checkpoints, those different gates or those valves along the way, it's the exact same thing. So in series, we could say that the current in the actual circuit is the same through every resistor. And you've seen this already in math, which I love, the fact that Mr. Hall taught you about series and sequence, because that's going to come up with notation here. What does the N stand for, do you think? Good. The last term or the last amount of resistors. So if there's 7 resistors in series, I equals I1 equals I2 equals I3 equals I4 equals I5 equals I6 equals I7. The current is the same through every resistor in series. That make sense? And think about it logically. If you don't have a split, it means the current is continuing. But in parallel, we're going to see in a minute, like a pipe, if a pipe splits, and it goes one way, this way, and then this way, what's going to happen to the water? It's going to go in both directions. Yeah, it's got to go in both directions. And the flow rate may not be the same in each direction. Depending upon several parameters in fluid mechanics, the same thing occurs here. So we're still in series, though. We'll get to parallel in a minute. Let's look at voltage next. Marco, read it for us. Next thing we have voltage.
We totally give out the fact that the potential difference across the battery is equal to the potential difference across the total load, sum of load across each resistor.
So in this case, what we can recognize is that the voltage is being split up to each bulb. Okay, the voltage is being split up to each bulb. A bulb with more resistance will have more voltage used by it. Resistance really means, again, the slowing and using of that energy. So if a bulb has high resistance, it's going to use more of the voltage. What law told me that? What law relates voltage and resistance? Ohm's law, very good. And Ohm's law says V equals IR. Well, I'm telling you a moment ago that I is the same for every bulb. The current for each resistor or bulb is the same. That was stated in the first part. If the current for each bulb is the same, but one bulb has double the resistance of the other, based on Ohm's law, it's I times R to give you voltage. So as a result, if you have more resistance, you have more voltage in that bulb. So what happens is as follows. You get this. You get the total voltage from the battery is equal to the sum of all the voltages. Different from the first one. The first one told us that the current across each resistor is the same. The current across each resistor is the same. Well, the voltage is not the same for each resistor. If the resistor has a higher resistance, it has more voltage. That's a little side note you probably want to write down. Okay, in series, as the resistance of the bulb or the resistor increases, the voltage increases. So if I have a battery that provides 9 volts, and the first bulb uses 7 volts, how much are left for the second bulb? What is it? Thank you. Okay? Again, it's the sum. Just illustrating that it's sums. So if one bulb uses 7 volts, and the battery is 9 volts, the other bulb has to use 2 volts of energy. So far, so good? Okay. All right, let's look at, in this last part, resistance. Resistance. And what we're going to talk about here is what's called equivalent resistance. Rach, why don't you read for us what we have for resistance?
Resistance, equivalent split out, V equals IR applies to each resistor. Thus, for two resistors in series, V equals V1 plus V2 decarbonizes.
So let's fill in this blank. If I could use V equals IR for voltage, right? If I want to figure out in general here what's going on, what can I replace these values with? What can I replace these values V1 and V2 with? What can I call them instead? What's the equation for Ohm's law? What can you replace V with? What is it? Good. I1R1, we'll say it that way, plus I2R2. Again, the last thing told us that the total voltage in a system is the sum of all the voltages. The voltage across the first pole, plus the voltage across the second pole, plus dot, 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 and how many volts there are gives you the total voltage. So here what I'm going to do is I'm going to replace V1 with I1R1 because of Ohm's law. Ohm's law tells me V equals IR. So I'm literally replacing the V1 from earlier right here with this statement. And let's assume that we only have two resistors to make it simple for the first example. We'll see more examples in a little. Well, if this is true, okay, if this is true, I can also denote the fact that what do I know about I1 and I2? What do I know about I1 and I2? Why are they the same? Yeah, that's the way the current works. So we just came up with the beginning. The current in series are the same. So if I1 and I2 are really the same, what do we write them as instead of subscripts? What do I just write them as? Yeah, just an I for each. Okay, not 2 times I, guys, not 2 times I, but an I for each. Like, remember how if mass, if the two objects are the same mass, what do we call the mass? Instead of M1 and M2, we just call them both M. So if the currents are the same, just call them both I. Now, if two things are the same, and they're in both terms, what can I do to it? Not cross it off, be careful. Take them out front, what's that called? Not canceling them. Opposite of distributive. It's the opposite of distributive. When you take something out front, you call it. If you have a quadratic and you write it as, instead of the quadratic, you write it as x plus 2x minus 7, what is that called? Factoring it out. Thank you. We need to know our words, guys. Factor out an I. Okay, factor out an I, giving you the following statement. Now, what does this tell us? Okay, let me explain what's happening here. On the side, draw yourself a little battery. Draw yourself 2 resistors. And then close the circuit. Draw it in red, please. Now, inside of any appliance, there are a multitude of resistors. Okay, there are a multitude. It's not one resistor. The appliance itself utilizes that energy in several different capacities. So as a result, you have several different resistors, really, in an appliance. But when you give a rating for an appliance, you don't say, well, the resistance of this appliance has 27 resistors, and this is what they are. You come up with what's called an equivalent resistance for that appliance, an overall resistance for that appliance. And if we look at what we've written here, we've written that the overall voltage, this is total, if you want to write the word total, maybe it'll help. Okay, the total voltage, we started by writing that it was split up for each resistor. For example, an air conditioner. Part of the energy is used to move the freon through the cycle. Part of the energy is used to display the electronic signal. Part of the energy is used to continue to keep the thermostat at the right temperature. There's many different uses of that voltage. So that's what we started with. The overall voltage used by the appliance, air conditioner, is split up. We then wrote it as V total equals I1R1, I2R2. But then recognizing that the current, if it's in series, is the same for each of the resistors for the air conditioner. Every resistor is using the same amount of current. So we're able to factor out that current. So in the end, what happens is this. The overall resistance of the circuit you would want to write like this. We call that R equivalent. Simply put, REQ. So what we can do is we can take that circuit that I drew in red up there, and we can replace both of those resistors with one what's called lumped resistor. Take the two resistors and simplify them into one resistor. That's what you're doing. It'd be like, imagine you have a spring and you connect another spring to it and connect another spring to it. You could probably model that as one spring, right? They're all linked together to one another. It turns out, and we didn't really go into this with springs, but spring laws are the exact same thing as resistor laws, and they're also able to be written in parallel and series, like we're going to see here. So what we do is we transfer or translate this diagram into something that's called REQ. So the goal of this section is to do the following. Take a complicated circuit and simplify all of the resistors into one lumped resistor. And it turns out, and we can see this here, that the equivalent resistor in series, see this right here, REQ, is really R1 plus R2. It's the sum of the resistances. The sum of the resistances. Okay, because again, I'm going to point to it in case you didn't know what I'm talking about. Because REQ is the equivalent resistance of, say, the air conditioner, and let's say the air conditioner has two resistors in it, it doesn't, has many more. We can see, though, that the equivalent resistance in series is the sum of the resistances. So our statement for resistance is the following. Okay, very similar to voltage. The same exact law applies for voltage and resistance when in series. When in series. So if you have 4 light bulbs connected and their resistances were like 2, 4, 6, and 7, you could simply add those 4 together, write them as one bulb, and you would have the equivalent circuit. It's like a simplified circuit. You never see every internal resistor unless you need to in a circuit diagram. Yes?
Is that your RS on your formula sheet? It says RS equals 1.
Yes. R for series.
Okay.
And then you're going to see RP on the formula sheet for parallel.
Okay.
Okay? Let's look at an example of what I'm actually doing. So let's take a look at this example, please. Mullen, why don't you read it for us?
A 9-volt battery is connected to 4 light bulbs, as shown in the figure to the right. Draw a schematic representing this and then find the equivalent resistance for the circuit. From this, determine the current in the circuit. Then find the voltage drop across each resistor.
So we've got a lot of information here. We need to draw this as a diagram first. So I need a schematic. Take about, 15 seconds. Draw what you think this should look like. You know your symbols. You know the battery symbol. You know the light bulb symbol. You should know what wires look like. So physically try and draw what you see in this diagram, but use right angles all over the place instead of, a little nice circuit, a nice circle. Use right angles for your wires. I'm going to do it like one step at a time as you guys do it. I'll start with the battery, but you should already have this.
When you do the wires, it's just considered one wire, even no matter how many corners.
Even if it's a corner is still the same wire.
Okay.
It's only if the wire splits in parallel, we're going to see where that's more than one wire. All right, so we talked about how we look at the positive flow, really. So let's start by coming out of the negative end. It doesn't really matter. Okay, then I'm going to go out the negative end. Now, I don't know which of these terminals is positive or negative. For the sake of this, I'm going to do this. I'm going to put a positive there and a negative there. All right? I'm doing that in the diagram up there. I didn't know which terminal was positive or negative. In the diagram, though, I know that the smaller is negative, the larger line is positive. Always. Always, always. If you forget that again, think about a plus sign, stacked on top of itself, makes a longer line. That's like a plus sign here, but both ends of the plus sign, both directionals. So after the negative terminal, we follow the flow. What does it hit first? How many ohms?
7 ohms.
A 7 ohm light bulb. Then what happens?
It's 5 ohms.
Hits the 5 ohm bulb. Should I turn yet? It doesn't matter. It's up to you.
No.
Not yet. All right. So not yet. Let's not turn yet. I'm going to turn after that. So now I'm going to turn up here. And then we're going to look at the next one, which is how many ohms?
4. Okay.
4. And then finally the last one. It really doesn't matter if I drew all 4 of these on the bottom length and then had 2 empty, whatever, wires. Because they're still on the same circuit. There's nothing that's changed here. If it's in parallel, then it does matter where they're located. In series, it makes no difference if they're all in series. Any questions so far? This was kind of like what you should have been doing with your homework when you were given an example and told to draw a circuit of it. Next, yeah.
On the diagram, does it matter if the positive side is up or down?
Technically, no. It makes no difference. No. And unless you're given in the diagram which is positive and negative, it wouldn't have mattered if you had done 7, 5, 4, 2 in that direction. For this case. I designated it on the diagram just now. So to be consistent, we did that. Now, what do you know about... Well, let's see. That's the first part, right? Draw a schematic. So we're done with that. Then what does it say? Find the what? No.
Current. No,
And the equivalent resistance.
Find the equivalent resistance. So that means take these 4 light bulbs, replace them with 1 light bulb that would have the equivalent resistance. And a moment ago, we wrote down a law. We wrote down the following. We said that resistors in series are equal to the sum of the resistances. Okay, what do we get? 18 ohms. Okay, the sum of these 4 is 18. So here's what I draw now. Go ahead and draw this, please. Okay, that's the equivalent circuit on the bottom. So what you're doing is you're literally taking something and just simplifying it. So that if somebody wanted to read about the appliance or understand it, and they were fixing it maybe, they understand the entire resistance, and then if they need to, they can look at more specific diagrams, such as the one at the top, to understand each individual resistor in the circuit. So you start with a general idea, if you were studying this element and you were fixing it, if you were, say, an electrical engineer or you were designing something, and you can then look at more specific diagrams here. Next. How many volts is the battery? How many volts? What does it say?
9.
So let's label that, please. We'll label 9V next to each of our batteries in the simplified and regular one. Okay. What can I find in high voltage and resistance? Current. And the current in the entire circuit needs to be the same. So write yourself a little note, please. To find the current in series, you have to first find the equivalent resistance like we did. You cannot just go ahead and find the... Well, I shouldn't say that. You could find the individual current of each of them. No, you can't. No, you can't.
But if you're in series, you have to.
There you go.
Well, let me see. I'm trying to think if I could do it separately. No, you can't. I'm gonna explain why in a minute. Let me explain why in a minute. It looks like you can at first. So let's go ahead and find out what the current is. The overall resistance, which we did. So we've got, for the current, solve for I. It's just V over R. The overall voltage of the circuit is 9 volts. The overall resistance of the circuit is 18 ohms. What's 9 over 18?
2. 1/2.
Thank you.
1/2.
Come on, people, that's the most common mistake, and I see a lot of you do it over and over. That's the current throughout the entire circuit. Now, if you tried to find the current for each individual bulb, you would not be able to do that, because each individual bulb does not take 9 volts of voltage. Think back to your voltage law. Go back to your last slide. What did it say about voltage? What did it say about voltage in series? What is the voltage law in series that we just wrote down?
Sum of the load.
It's the what?
Sum of the load.
The sum of each voltages. So if one bulb uses 2 volts, another one uses 3, another one uses 4, the other one, the end, would have only 2 more volts to give you 9 total. So each bulb uses a different amount of voltage. You don't know what that voltage is yet. But now that you know the current for each bulb, and you know the resistance of each bulb from the beginning, you can find the voltage across each bulb.
So you just divide each volt, not each volt, each ohm by 0.5?
Well, you multiply, right? Let's take a look. If I want to find the voltage across the first bulb, here's what I do. What is the current in the whole system now? What's the current in the entire system, no matter what? 0.5 amps. The current is the same for every resistor. This is part of our statement we made on the previous slide. So this has got to be 0.5. But what's the resistance for the first bulb? Well, let's assume we're going out the bottom terminal counterclockwise. What was the bottom resistor we had in the original diagram? 7 what? Ohms, right? So what's the voltage across the first bulb going to be? What is it going to be? 3.5 volts. That's the first bulb's voltage drop. How many volts are in the battery though?
4.
In the battery, how many volts? 9. So could this number have been bigger than 9? Would it have made sense? How could you get more voltage out of what you're supplying, right? So this is the voltage across the first bulb. The second bulb is the same current, 0.5, but instead of 7 ohms, how many ohms? 5 ohms. So we're going to get a voltage for the second one of 2.5 volts.
So on the test, I just this one of the last questions, right?
Yeah, this would be one of your end questions. Yep, absolutely.
What is the test? So,
When is your test? Monday? Yeah, reviews Friday, test is Monday. We have lab today. It's what? Thank you. Lab today. Finish up part of a lecture tomorrow. Review Friday, test Monday. 19 and 20.
So they're just all going to add up to 9.
What are they going to add up to?
9.
Very good. Very good.
I was not.
Like a deer in headlights.
why did you get so excited? You just said that.
Because you don't always notice it right away, but she picked up on the fact that these 4 actually add up to 9.
Yeah, we said it.
I said in general, but not specifically these 4.
I thought it was like a general rule.
So we had 7 ohms, then 5 ohms, then we did the, let's see, 4 ohms, and then V4 is going to be that times, what was the last resistance, 2? So look at your 4 voltages, please. And as you noticed, as we stated, yes, that is true, they do add up to 9.
But didn't you say you don't have to write, didn't you say you don't have to keep writing I or 2 or 3 because it's the same?
Sure. Yeah, so you can write it as I. 3.5 and 2.5 gives you 6, and 2 is 8, and 1 is 9. The sum of the 4 voltages gives you the voltage supplied by the source. Does this make sense so far, the idea? You need to make sure you're focused and listening when we go over the theory. Because some of you really weren't focused in the beginning, and I saw blank looks, and then you're scrolling up. You need to understand what we're doing here. Voltage is the sums. Resistance is the sums. Current is always equal throughout the whole circuit. Okay? So for resistance, again, sums, voltage sums, current equal for all. It's going to switch for parallel. You don't have to memorize these. They're on your formula sheet. So if you need to understand what I'm referring to, open your formula sheet. You're going to see these formulas on there. You'll see IS for series. equals I1 equals I2 equals IN. And you're going to see Vs, so that's your voltage, equals V1 plus V2 plus Vn. And then you're going to see Rs equals R1 plus R2 plus Rs. Those are all on your formula sheet. Okay? Statement. So, when you think about one bulb, if one bulb goes out, they all end up going out. Why is that in series? Physically look at what's happening in this diagram. What's happening? If a bulb goes out, what's physically happening? Ladies, what's physically happening? The circuit is no longer closed. How can the electrons jump from the wire across without a filament? So imagine the bulb goes out, the filament breaks, there's no longer a closed circuit. Okay? Is that clear? The minute any bulb goes out or any resistor goes out in series, it's no longer a closed circuit, so all of the bulbs are going to go out. You need to have electricity flowing through from one terminal back to the other. As soon as there's no connection here, this is not going to continue to flow through here. Everything just stops flowing.
Is it possible to have a light fixture that looks like this, but that is not a series? Because I have a light fixture that's in my bathroom where the lights are.
Oh yeah. So all the light fixtures look the same. They all have this, but the wires could be wired differently behind the scenes. You might see like 5 bulbs, and one of them may have gone out and the other stay. That means that they're hooked up in parallel. That's the wiring behind the circuit that's occurring, not just the way it looks physically to you. Okay?
Why would you want to set it up like that if it's so...
You wouldn't. For a long time, most things were only in series. When the idea of using parallel circuits became more useful, they started making combinations of them. Series circuits are very good if you want to regulate the current through them. Okay? So if you don't want it to overheat, for example, on a Christmas tree for a long time, your Christmas bulbs are always in series. Because to avoid a short circuit and the tree burning down and the house catching fire, you can regulate the current through it with series more than you can with your parallel circuits. Okay? So usually most things are a combination of both. So we're going to look at parallel in a moment now. Okay? Any questions on series beyond what we've answered already? All right, let's go to parallel. 2 seconds.
The sum of the currents across each resistor is equal to the current leaving the battery, and the flow rate through pipelines that may branch off.
So think about this as a pipeline that branches off. If you have 4 gallons per minute of water flowing, and then suddenly it branches, one pipe might get 1 gallon per minute. What does the other one get? 3 gallons per minute. Okay, think about branching off. So instead of current being the same like it was in the previous one, now the current is a sum law. So we're going to write it like this.
How is it different?
What did we write for series, guys? What was the law for series? It looks similar, but it's not.
Oh, it's equally.
Yeah. In series, it was all equal signs. In parallel, like we're seeing here, it's the sum of the currents. So, write this down. Put a little asterisk. Each resistor gets a different amount of current. Each resistor gets a different amount of current in parallel. In series, they all got the same. That's the difference. That's what this law is actually stating, that the sum of them is equal to the overall current. Next, voltage. Voltage. And this one is a little bit different. Okay, it's a little bit difficult to understand, so I'll try and go over it with us with a little diagram. God bless you. No? Okay, so I'll sneeze coming. Peter, you want to read for us?
Yeah. Voltage. Consider the fact that the positive terminal of the source is connected to one side of each bulb, and not just the first bulb as in the series.
Okay, give me. Actually, let's pause, and then we'll come back and finish these notes before we do the lab. Get it? So think about a parallel circuit. The way a parallel circuit is oriented is as follows. The surge or the power leaves the bulb or leaves the battery, enters one bulb. But what happens is this. This gets branched off and goes to another bulb, which is branched off to another bulb. this is what a parallel circuit looks like we saw in the beginning here. What's physically happening really is this. This is what's a little bit difficult to see. The negative lead over here is technically attached to every bulb by the branching aspect of it. So this negative terminal touching this terminal, touching this terminal, touching this terminal is what allows us to understand the concept that the voltage across each resistor is the same, opposite of parallel. So we've kind of switched up our voltage and current law between parallel and series there. Oops. So if you want to write yourself a little note, the current and the voltage, those rules for parallel and series are just switched. Okay? The current and the voltage laws kind of flip-flop when you go from series to parallel. Resistance is not either one. Resistance we'll talk about. Okay, now, with the first and second statement, I hope we're all focused. I'm seeing a lot of intent eyes. Let's focus up here. So in the third part, we're looking at the resistance. And if we're looking for the equivalent resistance, we can remember that we can write V equals IR, solve V equals IR for I. You get I equals V over R. Agreed?
Yeah.
The current law at the top, we're going to look at only two resistors. Look at the current law, it's the sums. So the overall current equals the sum of them. So if I know that current for the overall circuit equals the sum, I can replace I with V over R for these two spots now, like we did in the last one. Replace both of these with V over R. And we're only doing it for two resistors to make it simple, but this could extend again to infinite resistors. All right, now, the next part that's going to be a little bit tricky. Replace I with its equivalent, V total over R EQ. Remember, this is the current in the entire system right here. So we can replace it with the total voltage in the system over the equivalent resistance of the entire system. Again, all I'm doing is taking this formula and plugging it in here. But I'm calling this REQ, because when I'm looking at the overall current, I'm talking about the overall resistance and the overall voltage. These are the pieces of each one. Now, what do you know about voltage? You also know this right here. V1 equals V2, which equals V. So instead of calling these V1 and V2, what should I call them? Just V. So in this step, I've done two things. I've substituted for current with overall voltage divided by overall resistance. I've also replaced V1 and V2 with just V because they're all the same. Now, V is the same, and in every term, what can we now do? You can cancel here. Technically, you're factoring it out and then canceling, but you can cancel in this circumstance. So cancel all the V's. What's left behind when you cancel something?
1 over.
1 over. Very good. So what does this statement tell us? This is a little bit tricky. Instead of the resistance of the whole system being able to just add them up, you have to add their what?
Inverses.
Either word, very good. Reciprocal or inverse. This is called the reciprocal resistance identity, or reciprocal resistance law, or inverse resistance. Doesn't matter, either one's fine. Okay, but this is the idea. To generalize, we can write plus. All right, to generalize, put a plus, ... 1 over Rn. So if you want to find the overall resistance in a circuit, you need to add their reciprocals and then solve for REQ. We'll do that in an example real quick. Okay, so this is different than all of the laws. But again, you don't have to memorize any of these rules we came up with. So even the theory, scroll back up. If you forgot that the current in parallel is the sum of all the currents. Just look at the formula on your formula sheet, and that should tell you. If you forgot that voltage is the same because it's connected to each of the bulbs, just look at the law on your formula sheet. Do you see how your formulas help you with the theory of this part?
Yep.
What is it law? It's the resistance.
I'm not going to ever use it by name, but the reciprocal resistance law for parallel circuits, really. All right, let's look at another example. Identical example as the last one. What's the difference now? Look at the arrangement. How are they arranged? In parallel. Okay, take a look at the way it's arranged. This one goes to here, then this branches off going to here, which branches off going to the next one. So we're going to see all those branches. Let's draw a schematic of this, please. Let's draw a schematic of this one. Connect it to the first bulb, please. Here's your first bulb. And this one should be 7 ohms. It shouldn't be anything, and this is 9 volts again. But the first one definitely should be 7 ohms. Now, the wire technically, follow the wire in the diagram. Okay, and we'll see where it comes up in the schematic. Follow this wire. The wire technically comes from the bulb, look where I'm pointing please, from up here, and loops into the next one. So the wire technically comes from here and should go out like this into the next one. That's where this branch looks like. That's why that branch branches off like that into the next bulb.
Oh, it's that way.
Joy, what's up?
Should it be horizontal or vertical?
It doesn't matter. It doesn't make a difference. Yeah, I had some sunflower seeds during the break and I was choking on it. So this next resistor or bulb is 5 ohms here. Then what happens from the 5 ohm bulb is it branches off into the next one. So draw yourself another branch coming off here.
Does it get bigger and bigger, or is that just
No, it's just me drawing it out of scale. And then the last one also. So in the end, this is what it will all look like. Okay, we have 4 bulbs drawn in parallel. The flow of this circuit would come out the negative terminal. We look at the positive flow, which is the tradition. Comes out the negative terminal, and it hits here, and it splits. Part of that current falls back in. The other part gets to here, it splits. Part of that current flows back in. The other part gets to here, it splits. Part of it goes back in, and then this returns the whole way. All right, that's our first part. So we're done with that. Next, find the equivalent resistance in the circuit. So you can't just add them together anymore because they're not in series. The law says to do 1 over. So let's literally write the law out. The law says 1 over the resistance of the whole circuit equals the sum of 1 over all the resistances. So write them each over, or each of them under 1. And the 4 resistances are 7, 5, 4, and 2. So I'm literally just plugging into the parallel resistance law. That's all I'm doing. Now, with that said, how am I going to get REQ by itself? It's in the denominator right now, right? I can approach this like 3 or 4 different ways.
Can you multiply it?
No multiplying yet.
You have to get the common denominator.
You can start with a common denominator. That's one way to do it.
So
You could find a common denominator, simplify this as a fraction. Say the fraction, hypothetically, say the fraction comes out to be 2/9. And you have 1 over REQ. You could flip this and set REQ equal to 9/2. Or you could invert both sides. Or you could literally just take these fractions in your calculator, hit enter, and then use the x to the negative 1 key to get the inverse. If you were to add these 4 fractions together, I don't know if I did it or not with a common denominator. Let me see if I did. I did not. I did it because I assumed you're going to use calculators. I added these 4 fractions together, and I got approximately 1.09. Think about it logically. What's a half? 0.5. What's a quarter? 0.25. A fifth is 0.2. A seventh is 0.14, I think. So we're looking at here, 0.5 plus 0.25 plus 0.2 plus point whatever that is, I think 0.14. Add those together, you get 1.09. Now, had you done it with a fraction? Can somebody tell me what you get?
It's greater than that.
No.
Give me the answer. Just hit math, enter, enter. Hit math, enter, enter. What do you? What is,
153 over 140.
153 over 140. So this is really 153 over 140. Are you going to want to come up with a common denominator of 140 here? So what are you going to do? Which way?
Calculator.
Definitely calculator for this. Absolutely 100% calculator. If the resistors were like 2, 4, and 8, that's an easy common denominator. It's just 8. But the minute you have a denominator of 7, another one of 5, another one of 4, trying to find a common denominator for all 4 of these is really, really messy. 140 is really the product of all 4. It's all it is. Or actually it's the product of 7 times 5 times 4. Now, use the method with the calculator. So you get 1.09. But that equals 1 over REQ. So to get REQ, I have to do 1 over 1.09. Remember, folks, all you're doing is flipping these two spots. Switch these two spots. How do you do 1 over something on a calculator? No, make it easy. There's a key on there that designates that. So you did all this work. You got 1.09 with a bunch of decimals, right?
Yeah.
Hit x to the negative 1. It's right below math. And then hit enter. That gives you the reciprocal. That gives you whatever 1 over 1.09 is. What do you get?
140 over 153.
I know, obviously, but give me the decimal then.
Oh, I don't know.
Hit math, down, enter, enter.
0.92.
1.09. I'm doing something. Not 0.915.
That's it.
I mean, you could do 1 over 1.09 and you get, I got point.
Yeah, 1 over 1.09, you're still going to get 0.92. Absolutely. What's interesting about this?
1 over 1.09.
What's really interesting about this?
I got it like
Where's all your fractions?
What is the...
It's going to exceed your battery voltage.
Okay, so that's your
It's going to
fraction.
be way less than your battery voltage.
Right? Hit the button below math.
See, it'll be way less.
That button, hit enter. You're going
Somewhere
to
in
put it
there.
on
It's going to exceed your battery
Um,
voltage.
two. If you're confused, ask your neighbor on your calculator. You should be practicing.
What is the pattern that follows?
What do you say?
What do you want to be on?
Ohms,
You
ohms.
can do it either way, or do you want to explain?
No, I want it like this for sure.
Yes. Okay, the 1 over REQ is equal to 1.09.
Correct.
Okay.
Correct.
So
1 over there are 2 equal
So
that.
where does this ohm fall in place of the battery voltage?
Okay, so we're going to get to that
Is
in a
it
minute.
exceed or
Yeah.
is it less than?
What do you notice about the resistance here? Its value is either greater than, equal to, or less than the other resistances.
You didn't give an answer.
Okay.
Just gave the option.
I'm going with what greater than.
The equivalent resistance we get for the circuit, we took 4 resistors and we made 1 out of them. This is less than, greater than, or equal to the individual resistances.
Less than.
Equal to.
Less than.
That was all 3.
I got all 3 answers, yeah, so let's go through this. The original resistances were 7, 5, 4, and 2.
Yes, less than.
Oh, wait.
Less than, less than. I heard it from some people, but I heard same, equal to, or greater than.
So it's always going to be less than your other.
So REQ will always be less than any of the individual resistances. Okay, that's something you should jot down. These are little like tidbits. Because if you got an answer bigger than any of the original resistances, it doesn't make sense. So if you want a very low resistance appliance, how should you arrange them?
In parallel.
In parallel. If you want a high resistance appliance, it should be in series. Remember, series, all you do is add them together. So we got 18 ohms in the first example. We're doing the exact same example, but now in parallel. Instead of getting an answer of 18 ohms, we get 0.92 ohms. So parallel circuits result in low resistances. Okay, these are little fun facts. Things that if you actually ever went into designing a circuit, or a simple circuit, say you wanted to make a computer or do something on your own, these are good things that you would want to know. All the, what is this? The intro to electrical engineering. That's really what we're doing here. Now, that's the overall resistance. So please do me a favor, draw a new circuit. Draw yourself a new simplified circuit. This is the equivalent circuit to what we started with. We took 4 parallel bulbs and rearranged them into one equivalent bulb with a resistance of 0.92 ohms. If that is true, which clearly is, let's find the current. Let's find the current for the whole system. We know the current is not the same for everything, but at least we can find the current coming out of the battery. And then we'll figure out how to split it to each bulb. So let's find the current coming out of the battery. Here's my circuit now. So what do I use? What law?
V equals I.
Yep. To find the current coming out of the battery, I need to use the equivalent resistance. So take 9 and divide it by 0.92.
9.7.
What was the current in the last example when it was in series? Look back, please. See what the current in the whole system was in the last example. What did we get? Wasn't it like 0.5 or something?
Yeah,
0.5 exactly? Yeah. So in series, what do you notice? The current is very, as opposed to resistance, which was very high in series. What do you notice here? Resistance is low, current is much higher. Okay, so these trends are not coincidental. Okay, they're not coincidental at all. So again, it all goes back to design. If you want to design something, what setup should it be? Should it be a combination of both? Which is what section 20-3 is about. Okay? Now, if this is true, we know the voltage across every resistor is the same in parallel. So let's find the current for each resistor and see that when we add them up, we get this number. So let's start with resistor number 1. Let's find the current through resistor number 1 first. Remembering that the voltage in parallel is the same for all resistors. What was the voltage out of the battery?
9.
So it's 9 for every resistor. What was the first resistor? Wasn't it 7?
Yeah.
9 over 7 gives us, what do you got? 1.3?
Yeah.
That's my current through the first resistor. Remember what we said. Think about this like water flowing through a pipe. If the water branches off, some of the volumetric flow rate goes here, some of the volumetric flow rate goes here, same as current. You started with 9.8, but this first resistor, since it had a very high resistance, got very little current. Let's look at the next resistor now. If we're looking for I2 now, it's going to be V2 over R2, which is 9 over 5, which is
1.8.
1.8. Notice, the resistance is less, so the current is greater. That's because the resistance and current oppose one another, right? That was what you answered on your quiz. The difference between resistance and current, they are opposing forces, if you will. Not really forces, right? So, saying. Next, I3 is V3 over R3, which is still 9, but now it's over, what, 4? 2.25. And finally, I4 is V4 over R4, which is 9 over 2, which is 4.5. Add up those 4 numbers. Round it, please. It's not going to be exact because we rounded it. But add up those 4 numbers. You should get approximately 9.8 amps. Okay? Proving the fact that the current in parallel equals the sum of the 4 currents that each resistor takes on. All right? Awesome, guys. Very good. Let's summarize the last two things. These are no more math. Just in parallel, what would happen if I lost the bulb?
It would all go down.
No, they wouldn't all go down. That's the crazy part. Watch. Remove this bulb from the
It
circuit.
goes in both
That they would
directions.
still-
It's still complete circuit, isn't it? It still opens at one end, flows through the wall, and comes back. There's a gap there, so this bulb would go out, and all the other bulbs might get brighter. Okay, and you'll see that in the lab today. You're going to see how that works.
I think that's what happens to my lights, which is weird.
Yeah, they may or may not get brighter depending on the way it's controlled. At home, it's different. You know, simple circuit you'll see today. Okay, but if one bulb goes out, they still remain lit in parallel. So this is what you have at home for the most part for any sort of lamp that has multiple bulbs in it. They're always in parallel. It wouldn't make sense to be in series. If you lose one bulb, you got to suddenly replace them all. Or you have to replace one before you can use any of the others. To summarize, take a look real quick. This is your summary sheet. Okay, series, they're one after the other. Parallel, it branches off. Current. Notice, equal current for series, equal voltage for parallel. Sum of voltage for series, sum of current for parallel. And then the last one is the one that's a little bit different. Okay? That's your summary. So what I want you to do real quick is to break into 4 groups, please. 4 groups, I'll let you pick. Okay, 4 groups. There are 17 of us here.